The viperfish jaw doesn't open wide because it's flexible. It opens wide because its skull literally comes apart, exactly the opposite of what most anatomy textbooks claim about vertebrate predators. A force of 6,000 newtons per square centimeter from a fish with no chewing teeth. This is Chaliotis sloani, the Sloane's viperfish, a creature that lives between 200 and 1,000 meters below the surface, in a zone where the pressure reaches 100 atmospheres, the same pressure that would collapse a human rib cage in under 3 seconds. The viperfish doesn't just survive there, it hunts there. If you've ever watched a nature documentary and felt like the real mechanics were glossed over beneath a layer of dramatic music and slow-motion footage, you know how unsatisfying a beautiful shot feels when no one explains the actual engineering. The viperfish is one of those animals that gets shown as a curiosity, a monster of the deep with fangs too big for its mouth. The truth is stranger and far more specific than that. The official story most sources give you is simple. The viperfish has long needle-like teeth that interlock when its mouth is closed. It uses those teeth to impale prey. That's the cartoon version. The real structure of the jaw reveals something entirely different. A mechanical system that has more in common with a folding trap than with traditional bite mechanics. Here's what most people get wrong about the viperfish skull. The bones are not fused into a rigid frame like in most fish. The skull contains multiple mobile joints that allow the entire front of the head to rotate upward. When the viperfish strikes, the first vertebra behind the skull tilts forward by approximately 20 degrees. The upper jaw lifts, the lower jaw drops. The entire mouth cavity expands to nearly twice its resting volume. This is not flexibility. This is disarticulation, a controlled collapse of the skull's normal geometry. That moment of controlled collapse is the heart of the viperfish's engineering, and it is exactly the kind of hidden mechanics this channel exists to reveal. If you want to keep uncovering the real structures beneath surface-level descriptions of the deep ocean, subscribe to this channel. We do not stop at the cartoon version. Leave the word disarticulation in the comments if this single detail changed how you see a fish you thought you already understood. The specific bone at the center of this mechanism is called the hyomandibular. In most fish, this bone transmits force from the jaw muscles into the skull. In the viperfish, the hyomandibular is elongated and angled differently. It acts as a lever that pushes the jaw hinge past its normal stopping point. The result is a gape angle that exceeds 120 degrees, far beyond the 60 to 90 degree range, typical for predatory fish of similar size. But here's the thing. The viperfish doesn't need that massive gape to swallow large prey whole. Its prey, lanternfish, bristlemouths, small squid, are rarely larger than its own head. The extreme gape serves a different purpose entirely. It allows the viperfish to strike without creating a bow wave. In the mesopelagic zone, water is dense and viscous. A predator moving its head forward to bite creates a pressure wave that pushes water ahead of its face. Prey detect this wave through their lateral line system and escape before the teeth make contact. The viperfish's solution is biomechanical genius. Instead of lunging forward with its whole body, it opens its mouth so quickly and so wide that the suction generated by the expanding volume pulls the prey into the mouth cavity. The prey feels no pressure wave because the water is moving toward the predator, not away from it. Stop. Picture that distance for a second. The gap between predator and prey closes not because the predator moves forward, but because the prey is pulled into a vacuum created by a skull that can unhinge itself in 25 milliseconds. The opening speed is faster than a hummingbird's wing beat, faster than the neurological response time of a lanternfish. The bones themselves are adapted for this specific task. The jawbones of Chaliotis sloani contain fewer calcium deposits than those of surface-dwelling fish of comparable size. The lower density makes the bones slightly more flexible, enough to absorb the mechanical shock of rapid opening without fracturing. The teeth are not anchored in sockets. They are attached to the jaw by a thin layer of connective tissue at the base. This tissue stretches slightly during the strike, allowing each fang to angle outward by as much as 5 degrees. The outward angle changes the mechanics of the bite from a clamp to a trap. Once the prey enters the mouth, the teeth angle inward again, pinning the prey against the roof of the mouth. Research from the Monterey Bay Aquarium Research Institute documented these mechanics in 2013 using high-speed video captured from remotely operated vehicles in Monterey Canyon. The footage showed viperfish striking at prey less than half their own body length. The entire sequence, from jaw opening to prey capture, took less than 90 milliseconds. That is roughly the duration of a single frame of standard film. The ROV's cameras had to be operated at 1,000 frames per second to capture the motion at all. That 90 millisecond window is what separates a curiosity from a documented mechanism. This channel tracks every piece of evidence that closes that gap. Subscribe so you do not miss the next time a deep-sea predator reveals its actual operating principles. There are dozens more waiting at depth. In the comments, write 90 milliseconds if this footage changed how you visualize a strike you cannot see with your own eyes. If you've ever assumed that deep-sea predators are slow because of the cold and the pressure, you know how completely wrong that assumption turns out to be. The viperfish strike is among the fastest recorded movements of any marine animal relative to its body size. The speed is made possible by the same disarticulating skull that makes the creature look like a biological anomaly. The first malariform teeth, the long curved fangs that give the viperfish its name, are not used for chewing. They have no cutting edge and no crushing surface. They function as guides. When the jaw closes, these teeth slide past each other in an interlocking pattern that positions the prey's body directly over the mouth's central opening. From there, the prey is swallowed whole by peristaltic muscle contractions in the esophagus. The teeth do not puncture the prey's vital organs. They hold the prey in place while the swallowing reflex takes over. This design solves a problem that most predators never face. The mesopelagic zone is nutritionally sparse. Prey encounters are infrequent, often separated by hours or days of drifting. When a viperfish does encounter a potential meal, it cannot afford to lose it through inefficient capture. The skull is built not for repeated, low-stakes feeding, but for a single decisive strike that cannot fail. Every structural adaptation, the mobile joints, the flexible bone matrix, the angled teeth, the vacuum capture mechanism, converges on one functional goal: maximum capture probability per encounter. The cost of this specialization is durability. The jawbones of Choliotis sloani are weaker in absolute terms than those of surface predators. The hyomandibular lever system introduces mechanical stress points that reduce the jaw's ability to withstand lateral force. If a captured prey struggles violently from side to side, the jaw can dislocate permanently. The viperfish compensates by striking from below with upward momentum. The prey's own escape instinct works against it. Fleeing upward moves the prey deeper into the mouth cavity. The mechanics are optimized for a specific attack vector. Now the escalation deepens. The viperfish's jaw is not the only adaptation that makes this strike possible. The creature's entire body is part of the same system. The first 6 vertebrae are modified to resist compression during the strike. The swim bladder, which in most fish provides neutral buoyancy, is reduced to a fraction of its normal size. The viperfish maintains a slight negative buoyancy. It must actively swim upward to stay in its preferred depth range. This constant upward effort means the viperfish is always oriented toward the surface, always ready to strike upward at any silhouette that crosses its field of vision from above. The bioluminescent photophores along the viperfish's belly serve a dual purpose. They countershade the creature against the dim downwelling light, making it invisible from below. But they also function as a targeting system. When a prey fish passes overhead, the viperfish can adjust its strike angle based on the shadow cast against the photophore field. The light organs produce a wavelength around 470 nanometers, blue-green, which penetrates deepest in clear ocean water. The viperfish does not need to see its prey. It needs to sense the interruption of its own light field. Here's where the inversion becomes complete. The viperfish is not a mindless deep-sea monster that opens its mouth and hopes for prey to swim in. It is a precision instrument that calculates distance, angle, and timing using its own bioluminescence as a rangefinder. The jaw mechanism is the final stage of a system that begins with photon emission and ends with skull disarticulation. Every part of the chain is interdependent. The climatic reveal arrives when you consider what this means for how the viperfish evolved. The disarticulating jaw did not appear suddenly. It required multiple co-adaptations. the modified vertebrae, the reduced swim bladder, the photophore array, the low-density bone composition. None of these features would have been useful in isolation. The system had to emerge as a complete package. Evolutionary biology calls this a functional integration. The viperfish is one of the clearest examples in the mesopelagic zone of a predator shaped entirely around a single constraint: the need to capture prey without alerting it first. The name Chaliodus comes from Greek, meaning prominent tooth. But the tooth is not what makes this predator exceptional. The tooth is the visible symptom of an invisible mechanism. The real adaptation is the skull architecture that allows those teeth to function at all. Every diagram you have seen of a viperfish jaw drawn with the mouth closed is misleading. The closed position is the resting state. The functional state, the state in which the animal does its only biologically meaningful work, lasts less than 1/10 of a second per strike, and those teeth are angled outward, skull bones are separated, and the mouth is a vacuum chamber, pulling prey into darkness. The second layer of the resolution addresses the open question that researchers at the University of Tokyo's Ocean Research Institute are still investigating. The viperfish's jaw mechanism appears to rely on a cartilage pad at the base of the skull that has no known equivalent in any other bathypelagic fish. This pad may act as a spring to store elastic energy between strikes, allowing the fish to reset its skull geometry without muscular effort. But the exact biochemical composition of this pad has not been analyzed. The tissue degrades too quickly after death to be recovered intact by net sampling. The leading hypothesis is that the pad contains a unique form of elastin not found in any surface-dwelling vertebrate. If you register this mechanism as an optimized strategy that evolved under constraints you had never considered, you understand why the viperfish has been called the most efficient predator in the mesopelagic zone. The jaw does not open because the fish wants to eat. The jaw opens because evolution solved a physics problem that no other predator in the zone has solved the same way. The skull comes apart because that is the only way to pull prey into a vacuum without creating a wave. The bioluminescent field along the viperfish's belly dims as the creature drifts back into darkness. The photophores cycle through a slow pulse, searching for the next interruption. The skull has reset itself. The cartilage pad has recompressed. The hyomandibular lever has returned to its neutral position. The entire mechanism stands ready for a strike that may not come for another 6 hours. But when it does come, it will take 90 milliseconds and leave no evidence in the water that anything happened at all.